So,
Comencem?
Daniel, Andreu, comencem la presentació? Molt bé.
Bueno, pues, bon dia a tots, benvinguts. Good morning and welcome everybody to this edition of the Erasmus Summer School of Physics at the Faculty of Physics of the University of València. My name is Jordi Vidal, I am the Dean of the Faculty, and it is a great pleasure for me, and I hope also for you, to be here today in this opening of the fourth edition, maybe fourth and a half.
Well, fourth, but there were two that were half, yeah. So.
Of the school, basically in this room, with all of you here in person, after 3 years, or let's say, special editions. Remember the cancellation of the second edition in 2019 because of the pandemic, and the second and third edition in 2019 and 2020 and 2021 edition of the school that were online. So let's congratulate of being here, all of us, today, and wish the school will continue like this in the future. As some of you may know, and some others may not, in the Faculty of Physics, faculty members are grouped in 6 departments: Applied Physics and Electromagnetism, Theoretical Physics, Optics, Optometry and the Science of Vision, Astronomy and Astrophysics, Atomic, Molecular and Nuclear Physics, and finally Earth Physics and Thermodynamics. Each edition of the school is devoted to the topics related with the research and interest of the staff of 2 of these departments, as well as other topics of general interest. In the present edition, the departments in charge of the school have been the Department of Applied Physics and Electromagnetism and the Theoretical Physics Department, so the majority of the people in the organizing committee are from these 2 departments. These people are Carlos Miró, Daniel Queiroz, and Andreu Anglès Castillo, predoctoral researcher at the Theoretical Physics Department. Jesús Ortiga Fibla, Carlos Álvarez, predoctoral researchers at the Department of Applied Physics, and Martina Delgado Pinar, professor at the same department. And we have also the collaboration of 3 undergraduate students in physics: Carmen Galotto, Victoria Paul, and Francisco José Pérez. All 3 are in their 3rd year of studies in physics. I would like to thank all of them for the work and for the lot of time they have spent in the organization of this magnificent school. Thank you very much to all of them, and also to the presenters. On the top of them, there are 2 professors in the organizing committee I have to thank especially. There are Professor Enric Valor, Vice Dean of Studies of the faculty, and Professor Manel Perucho, here with me, Vice Dean of Quality and Mobility. They are the super coordinators. They are the general managers and the responsible. I mean responsible. If everything is a disaster, they are responsible. If everything is working well, I will be the responsible. Okay? Okay, seriously speaking, they are the general manager of the school from the 1st edition, year after year. Let me thank them especially because I really know how big was the task that I entrusted to them 4 years ago in the 1st edition. I very much appreciate their effort and the engagement to all editions of the school. Thank you very much. Without you, there would have been no school, I think. Now it's time to finish my speech, and hoping you will enjoy the school. I hope you will have fun, and also you will learn something interesting in the topics and in the sessions we have scheduled especially for you. And now let Manel to introduce the edition, and thank you very much to all of you.
Thank you very much, Jordi. I will be short, will be brief, and I just want to say that I am very happy that this edition counts on our visitors from the For Them Alliance, from Palermo, from Burgundy, from Jyväskylä, I think too, and from Latvia, and this is well, this makes us happy that we can share this school with you. So thank you for coming to visit us. The school is aimed this year to achieve more knowledge on applied physics, electromagnetism, and theoretical physics. We have talks from conductors, semiconductors, and many special devices that are used in accelerators, or you know, those of you who have some who are keen on cables and screws and so on will be happy with this. And also those of you who are not, but you like theoretical physics and you like more abstract stuff, like, I don't know, future quantum computation and so on. And then there is also something about the universe, on dark matter, on, well, there are also neutrinos, of course. We have always neutrinos here. And I hope that the talks are pedagogical enough that you can learn basic concepts. Sometimes, yeah, things can get tough during the lectures, but you can please ask, raise your hand and say, can you repeat that concept in other words so that I can understand something about it? Please do that. Don't hesitate to do it. And aside from that, well, we have planned a schedule with, which is easygoing. We have mornings, basically. Tomorrow in the afternoon, we will have a session on, well, people who have experience in different careers after studying physics, let's say teaching, say research in companies, or research in hospitals, and after doing a master on data science and things like that. I mean, so we want to show you diverse paths that you can follow, not only basic research, which is the main aim of the school, of course. And we will have this, and in order to encourage you to come, we will have some more chat and fartons after the session, so you can enjoy that, which is a local thing. I hope you like it. So then after that, we will have on Thursday another social event, which will be, we have a guided tour to the city of Valencia. So we will have, well, first we will have some kind of physics party here. There is a gang of students who have prepared a session with questions and quizzes and so on, some fun. And they are very active, and knowing them, we will really enjoy it. And then after that, we will move to the city, we will have a guided tour, and then after that, for those of you who want, we can go for dinner, so the school dinner, to a student place in Benimaclet, which is the student quarter per excellence. And then you can, yeah, we can have a relaxed evening there. So please reply to the email you got from Andreu some days ago to register to the dinner if you want to come have dinner with us. And yeah, that's what we have. I hope you enjoy the school. I hope you have a great time, and I really appreciate, mainly in the case of those of you who come from abroad, that you're here, and also from those of you who come from very close by too. So thank you very much, and enjoy the party.
Okay. Can we start? Okay. First of all, welcome everyone. It's a pleasure to meet you all in person after the pandemic. And of course, we are very happy to have you here in Valencia enjoying our summer school. Let me begin introducing our first guest, Maria Antonova. She is originally from Moscow. She got her bachelor degree at the National Nuclear Research University, Moscow Institute for Physics and Technology, specializing on experimental methods of nuclear physics. Then she continued with her scientific career at the same university, focusing on neutrino physics. For a master thesis, she joined the T2K experiment, where she met her current supervisor. That very much defined her scientific path. She applied for a PhD here in Valencia at IFIC, moved to Spain, and now she's about to deposit her thesis. We are glad to have you here with us today talking about neutrinos, which is one of the most active topics in both theoretical and experimental particle physics nowadays. And now the floor is yours.
Can you hear me, right? Okay. Okay, thank you very much for inviting me to give you a talk. And I've tried to keep it rather simple, but please stop me when I will be using too technical words or explaining in the very mumbling tone so you don't understand anything. All right, so I'm gonna talk about neutrinos and not so much. Okay, so when we talk about neutrinos, that's nice to start in the very beginning. And for neutrinos, the very beginning would be telling a little bit about what we call a standard model of elementary particles. I'm not quite sure if you're familiar with the concept, but so it consists of different particles of different types, and there's different type of particles. They can interact in the so different ways. And what we call to interact means to exchange another particle which carry the interaction. So in case of strong, what we call strong interaction, it can be a gluon. In case of electromagnetic interaction, it would be a photon. And in case of something we call weak interaction, it would be Z and W bosons. I will not talk much about these strong and electromagnetic interactions. Well, electromagnetic will appear later in the talk. But you need to remember that there is something we call weak interaction, and these Z and W bosons are involved. And they have direct connection with the leptons. So the electron, muon, and tau, and neutrinos, which are the main heroes of this talk. The last but not least and very interesting particle in the standard model is the Higgs particle, which everybody knows about it. And that finishes almost my introduction of the standard model. This is expanded version, so you see there are a lot of things to present, but I'm not going to stop in this. I'm not going to dive very deep into that because there are still 30 slides, and my focus are neutrinos. So let me share some, well, not funny, but nice fact about neutrinos. So why they're amazing? Because first, a nice banana would emit 1 million neutrinos per day. You, because of the radioactive process happening in your body as well, would emit even more neutrinos today. But all these vanish and disappear if you compare yourself to a star or to our sun, which produce trillions of neutrinos, and they pass through your body every second. I mean, right now I'm standing and there are a lot of neutrinos going here and there. And this would be nice, but I mean, there is only 1 out of 4 chance that neutrinos will interact within your body during all your lifetime. So it will take really a lot of time to make sure that for sure neutrino will interact with you and you will notice. Well, you will not, but anyway. So that's very probable story. And okay, but if they are not interacting, we don't see them, then how on earth we found these neutrinos? And that happened in the early 20th century. 20th century is basically the era of a lot of discoveries in the modern particle physics and what we study right now. Everything started with beta decay. What was expected to be just a picture of a lot of lines, so electrons with very well-defined energies from this from this process, turned out to be a huge and continuous spectra. So no lines. I mean, what's going on? Why there are no defined energies of the electrons? This is really weird, and it violates the law of the energy conservation. I mean, physicists doesn't like when something violates the law. It is like, it means that the theory is wrong. That means that you have to go back, start your work again, and this is annoying. So people said, okay, what can we do? Why, if something is, the law is violated, there should be explanation. And here came Pauli, and he said, okay, there are two options. Either law is violated, or we have a solution. There should be a particle, which would be neutral, because the charge should conserve. So neutral particle, and here we have positive charge, negative charge, meaning the last particle have to be neutral. It would have something which we call spin, which I will describe a little bit more later, as 1/2, also for some conservation purposes, and it should have very small mass, because again, when this process has been calculated, there was nothing expected, so the mass should be really small to match with the calculations. Okay, he called it neutron because it was meant to be neutral. Then Chadwick discovered the neutron, the true one, so like this, true guy, and Fermi called it neutrino. So in Valencian would be neutrinet, but Fermi was Italian, so we have a neutrino. And yes, but there was one problem with this neutrino. That was really hard to find. I mean, Pauli was saying, sorry, I invented a particle, you will never detect it, but I invented, so say thank you, your energy conservation law should be fine. Then people say, okay, we don't want the law to be broken, let's find these neutrinos. Neutrinos are invisible, so they're ghosts, and they invented the project Poltergeist to look for neutrinos through something called inverse beta decay, so the other way around. You try to make the neutron and to see the electron. Like, okay, they found it. Very well. But then there were more questions open. It's like science works like this. You discover something, and they discover more, and then you understand that you don't understand, and you go more and more and more, and you bump into the next question. While they were looking for neutrino, they discovered the muon. And they discovered the muon. They had to discover a muon neutrino, maybe, and they discovered it. But then there was one more question. Okay, how many neutrinos are there? How many neutrinos we should still have to find? And that was another topic to make an experiment for. And that was done for studying the lifetime of the Z boson, the boson from the standard model. It is meant to decay. It's meant to decay into neutrino and antineutrino, so particle and its own antiparticle. And the faster it decays, the more neutrinos you're meant to have, and then you just measure it, and the result that was obtained was close to 3. And thus there was a lot of searches, and if you want to find something, you will find it at some point, I guess. So they found the tau neutrino, but just like think about it, 20 years ago. So this is a very recent story. These people, well, potentially are still alive, for people who just found it. So it's not a historical course. It's happening now. So about neutrinos, what do you need to know to continue on this talk? I've tried to throw away as much theory as possible because I'm experimentalist and I'm really bad with that. So the neutrinos don't have color charge. That's something which goes about quark, which are not heroes of the story, so no. They don't have electric charge, unlike electrons, muons, and tau, so the leptons which they go together with. And they interact only through weak force. I mean, why? Because they don't have charge, and there is only weak force left. In the standard model. We are within the standard model so far. Yes. Okay, but this interaction is contained within the electroweak theory, and For that, I need to introduce you some more things. So the first is helicity and chirality. So what is helicity and chirality is, maybe you know, but I will repeat it. So the idea is the following. So you have momentum. I will not do it with my hands, I will do it with this. You have momentum of the particle, that is a vector, it's directed somewhere. And you have a spin of the particle. So if you want to imagine what spin is, but maybe you know, I don't know. So like the ball is rotating, it's rotating either there or there, like left or right. So that is the spin. But then to get helicity or chirality, but in case of neutrino, it's the same story. You project the spin on the momentum and then you get some direction, like one way or another way. And this what we call like right hand or left hand because, well, we like nice analogies. And, well, okay. So if you think about the parity operation, so you take your coordinates and then you flip them. In case of helicity, it's supposed to be fine. So it's like just changing, because if you look at this, so momentum is changing the other way around, spin is the actual vector, so nothing is happening, so it should be changing, right? But no. Because if there is some concept, you should check, indeed, if the real life, it is the truth. And no, there was an experiment which shown that, no, that the parity is violated, and violated very violently and very bad. So the theory was broken again, and that was not nice for many physicists, because we don't like theories to be broken. Thus, there were like a lot of explanations and a lot of takeaway messages from this experiment. So this means that the weak bosons would couple to the left particles and the right antiparticles. You cannot have left-handed antineutrino. That cannot exist if this experiment is correct, and it is correct, please. And they cannot be the other way around also. So, okay. That means that we are getting to this. So, and okay, we still fine with standard model. Everything is explained, and everything seems to work. But you know that there are a lot of physics beyond standard model, so there should be some catch. No, I mean, of course not. There was an experiment in the 1960s to just study neutrinos coming from our sun. The experiment very simple. Potentially you can repeat it at home, better not. So you take a lot of detergent with containing chlor, and then you leave it for some time, and you measure how much of the argon would be produced thanks to this reaction. Oh, sorry, yes, to this reaction. Okay, you wait for quite some time, and then you check. But when you open the box, for Davis, it turned out that there was not enough argon. I mean, what was going wrong? There was experiment wrong, he made it bad, something was, like argon was going somewhere else. Well, that was called solar problem, and people kept looking out. And next source of the neutrinos to study was the atmospheric neutrinos, sorry. They appear after neutrinos interacting in the 15 kilometers, they appear from the particles coming from space, interacting in the 15 kilometers above the ground. And in this so-called showers, you're getting the neutrinos produced. They come through the ground because they rarely interact. And then you measure, okay, but how much of the neutrinos you would get, given that you have some theory predicting how many there should be, like how many electrons, how many muon. And there was again some inconsistency in the results. So there was obviously something going wrong. So because you see something weird once, you think the experiment is wrong. You see something weird twice, it makes you think that, okay, probably my theory is not very much complete. And there were some probable solutions for that, because I mean you should solve it. If they have some discrepant, you have some glitch in your theory. So first option is that neutrino oscillates into antineutrino. And in this case, you say that neutrino can be their own antiparticle, something that's not happening to other particles. Well, not to any, I mean, photon is photon. So then it means that neutrinos are something we call Majorana particles. I'm not going into this because this is more theoretical question. Then, but I mean, if you are curious, you can read about it. There was also an idea of neutrino changing the handness. But this is like a concept of the sterile neutrino, and also very, well, not bizarre, but it's a topic now in the neutrino physics. But that's not, again, what I'm going to talk about. I'm going to focus on this. So this is the idea of neutrino oscillating to another type. So you have a neutrino, it does some magic, and then you detect muon neutrino. And, okay, so this free concept. And what was found, I mean, of course, I'm focused on the last one. So the last one was proven to be true by the experiment Super Kameokande in Japan. And what then confirmed by a snow experiment in the US, because, I mean, if you find something once, you don't believe it. You have to prove it once again. And this told us that neutrino oscillate. So they changed from one type to another. And there was a Nobel Prize given for that recently, and I mean, these people are still perfectly fine and alive and giving talks. So I strongly encourage you to find some talks by Takaaki Kajita, who was from Super Kameokande. He talks really nice about the way how they made the discovery and show a lot of cool photos. And well, after this advertisement, let's go back to neutrino mass. So they have mass, meaning the standard model doesn't work. That something is wrong. So they're supposed to be massless, but they're massive. And what does it mean? That not exactly the same way how neutrino have mass, how the other particles have mass. So there is the theory was invented to explain this mass because it was no standard model anymore. And like what we call mass is rather a difference between the states of neutrino. And why I'm saying states, so like neutrino is some sort of a mix of the free massive state. And why, I mean, the way how it mixes is described by this matrix, which we parameterize in the way we think is the best. And yes, so when we talk about neutrino mass, usually we talk about the difference between the mass states. And that's the first question which we study right now, which we don't know yet. Which picture is true? Which is it's normal or it is inverted. So far, we can say, okay, we give preference to one or to another, but okay, that's already an open topic. We already arrived to the present state of the neutrino physics. So going back to that matrix of the mixing between neutrinos, in the simple way, in simple case, when you have just two neutrinos, so electron and muon, you parameterize it this way. And when you want to get from here to probability of neutrino oscillating, and in this case not oscillating, you're getting something looking like that. What is important when you look, and then you make a picture, it would look this. What is important in this formula is to say first, if the mass is 0, then probability is 0. So once again, if neutrino are massive, they oscillate. Or, I mean, the other way around, they oscillate, thus they are massive. Second, there is something called mixing angle, and that defines the amplitude of this like probability thing. And then there are parameters which this probability depends on. That is the distance, so how much neutrino will travel within the matter or within the space, I mean, anywhere. And the energy of these neutrinos. So that's actually very important for our experiments, so keep this in mind, and I will talk about this a bit later. So when you have free flavors, the matrix starting to look a bit more complicated, and the formula also makes starting to look even more complicated, but that's what we are working right now in the conventional neutrino physics. So free flavors, no sterile neutrino, no Majorana, I mean, nothing like that. You just have this. And then you have something called mass splitting terms, so mass differences, so the difference between three different states. Then you try to measure it, and here I have numbers, but that doesn't mean that we precisely measure the number. It means that till some degree of probability, we measure this number to lie within the region, and with some error, it would be this. But this is not very confident. It's not very confident statement. It is just what we measure. And there are mixing angles. Again, so the same story. We measure them till some degree of probability, and we are kind of sure they're supposed to be there. And basically all answers experimental physics gives to you, they sound like this. Okay, so this matrix, there are neutrino oscillation parameters. And of course, you want to study them, you want to measure them. You can take different sources. So as I said, there was atmospheric problem, so neutrinos come from space. You have solar problem, so neutrinos obviously come from sun. You have reactor experiment, so you can take a detector, put it close to the reactor. This is the one close to Valencia. I'm not sure if they put any detectors, probably not, but you can do it. And this is you can also produce neutrinos in the most brutal way. So you just like, okay, I need neutrinos. That is what experiment I work in is about. So this I'm not going to cover right now, but in a couple of slides. So the open topics of this oscillation matrix are the following. So that's what we are looking at now. So this is a Nature paper published like 2 years ago during the COVID, and published by the experiment I work with. And the first question, which we are very curious to prove, we really want to get it, the CP violation. So if the neutrino oscillates exactly as its counterpart antineutrino. And so this is something we really look into, and we look into this in the question of, especially in the case of accelerator experiment, because there you can artificially produce very similar amount of like neutrinos and antineutrinos, like you do it in a very controllable way. The other question is the neutrino mass. As I said, you don't really know. You say that there is some degree of probability that neutrino mass is but you obviously don't know which neutrino is the heaviest one. So if it is like normal ordering, so first state, second state, third state, or is the other way around, that's okay. You need to put these neutrinos in some way. Or yes, so like this is like the big question. And and of course, neutrino don't get the mass from standard model. So how it gets the mass? There are really a lot of theories about that. I've been to a talk of some theorist from IFIC, and he said something like 200, but I throw the one I don't like, and I mean, so you can see the scale of the problem. So they have to, there is really a lot of work to prove which theory is correct. Of course, experiments help, but theorists are really fast creating these theories, so, well, there is a lot of work for that. Okay, so are there sterile neutrinos? So electron, muon, tau, and there may be something else. Maybe yes, maybe no. Then the question is of the mixing angle. So there is one of the angle which is very ambiguous. So you measure it 1 year, you get like less than pi/4. Then you measure it another year, and you change a bit some of your statistics, and then you're getting the other values. So that's also an open question, and we don't like to get some ambiguity because it changes the way how we perceive a lot of this neutrino theories. So it rules some out and allows another one to be true. What is the speed of neutrino? This, I think, there was a big, not like scandal, but there was a hot topic some years ago when Opera said, no, neutrino travel at the speed of light, and everyone was like, what? I mean, why? That's not normal. No, okay, neutrino are not normal in general, but, well, that was an overkill. So, but then they checked their data, it turned out that it's not true, but precedent had happened. So, in the remaining time, let me tell you a couple of words about the accelerator experiment, the T2K, the one I'm working in. So that is my research and what I was doing for my PhD thesis. So the last source of the neutrino, the one you can get the more artificial and the most controllable way, is the accelerator neutrino. So you take the ion, then you strip it out of everything to keep only protons. You put the protons to the linear accelerator, accelerate it more in the small ring, even more on the bigger ring, more, and then you smash it to the wall of graphite. And when you smash it, the protons interact with the graphite, and then they produced first the bigger particles, which decay in some smaller particles plus neutrinos. That's what you want. Then you put a huge filter, so like a gigantic concrete wall. That works, because neutrinos don't interact, everything else interacts. You put the wall, and then you get your neutrinos, and you measure it twice, because you want to see how many of them will oscillate. You measure it once here, near the detector. You have some fancy setups here. Then you allow them to travel, because you remember there was a distance in the formula. And then you measure them second time in another detector. But there are a lot of tricks, because you want to have the maximum effect. So you put your detector here in the maximum of the neutrinos. So if the theory is true, in the maximum neutrino oscillation. So if the theory is true, you should see you see a huge deficit of the neutrinos you first produced here, and a lot of neutrinos, appearance of the other neutrinos, you see electron here, the appearance of neutrinos of the other type, and that's basically what you see. So this was a present. That's the next experiment that is now under construction, that is called DUNE. Don't say Dune, please. I mean, that is horrible. DUNE experiment, and that will be in the US. It is meant to start operation by like 2025, 27, but everything will be built for sure, I really hope, in 2030. And as DUNE has a longer baseline, so this distance here is 1,300 kilometers, while in T2K you have only roughly 300, so this is longer. So neutrinos will not oscillate just once, they'll go, like, that goes to the next oscillation maximum in that formula, so in this one. Okay, so it goes, like here, there will be one more oscillation maximum, and there, where the DUNE will be measuring them. And it has more powerful beam. That means that you have more energy and you have more particles. So you have more statistics, meaning that you have more information about neutrinos. So you can more precisely measure everything which T2K can measure. So you can get even more strong statement about all these neutrino oscillation parameters. And of course, neutrino oscillation is already a study beyond the standard model. And all those experiments, they explore what can go even further. So all the sterile neutrinos, Majorana neutrinos, and I mean, dark matter, a lot of those things, everything can be studied with neutrinos. I mean, there are a lot of applications for cosmology, because neutrinos don't interact with matter, meaning that if something happens out there in the universe, neutrino will bring you information almost first, because it will just go straight away, and it travels really fast. So for the multi-messenger cosmology, for instance, neutrinos are very important. They're used for as like some alert signals to say, okay, there's supernovae somewhere out there. So yeah, all this experiment, as an example, which will, I mean, this is a very nice one, and we'll have a lot of projects in the future. So that was my PhD. So that is how Super Kamiokande looks like, by the way. We were repairing it in 2018, so like huge one. So that's what you do when you're experimentalist. And I hope if you will go for PhD and you will like neutrinos, you also have nice time. And if you don't want to ask questions right now, I feel uncomfortable, please send me an email, okay? And I will be happy to provide you any information you may need or answer your questions, or just ask right now, and thank you for your attention.
Wait, and I'll give you the microphone.
You said you can control the length in the experiment, the length traveled by neutrino.
This?
Yes, but you can control the energy, like slowing down.
Yes, I mean, the thing is that here you produce the neutrino artificially. So you have your accelerator, which is supposedly producing the neutrinos of the energy you need. The trick is hidden in this formula, in this one, please. So you need to optimize this ratio, how much neutrino will travel to neutrino energy. Of course, you can make it short, smaller, or bigger, but you really want to be optimize it as much as you want. But yes, you're free to tune anything you want.
Okay, thanks.
You're welcome.
If you have a question, please raise your hand. Okay, over there.
Hi, thanks for the nice talk. My question was about was it the Raymond Davis experiment? I just wondered, how did he detect 3 argon atoms?
Well, that is a very, very good question, which I'm not quite sure I'm qualified to get reply on top of my head, okay? Because this is almost a fact from Wikipedia, because this was like a lot of time ago. But of course, he was not looking at it with the, okay, let me open my chlorine detergent tank and so on. He was using some, I think it was some chemical reaction, so he was rather, so it was something like that. But okay. I really suggest you search it rather on Wikipedia.
Right. Okay, thanks very much.
You're welcome.
Okay. More questions? Okay, over there.
Is it legal to organize or so questions?
So you said that there are a lot of neutrinos coming from space. How can you detect those neutrinos? For instance, neutrinos coming from a supernova.
Well, first of all, you have amazing superconductor, so you can detect it. First, you expect them to have really high energy. You expect neutrinos to be something which was not really produced neither in atmosphere. If you have an accelerator experiment, so when T2K you have the beam which made artificially, but then you synchronize it with time. You say, okay, I shoot neutrino now, and you catch it there almost at the same time. So you have synchronization up to 9 nanoseconds. So it's like really, really precise. So and also the angle. Neutrino which would be coming from the accelerator will shoot it here. But neutrino which comes from the supernovae, which will go like here, I mean some random direction which you don't really expect to happen. But yeah, but the the biggest thing is that it should be rather a strong neutrino.
Thank you.
I mean, about Cosmic One, I think I deleted the backup. Oh, no. No, please. And that's about neutrinos coming, bringing information from sun.
Hi, I don't know if you answered this question, like if you said it during the presentation, but you said someone blasphemously said that the neutrino speed is the speed of light.
Ah, yes.
But it was wrong. So
yes.
Do you know the speed? Did they find out what the speed of neutrino is or not yet?
No. I mean, there are a lot of questions. So, like, we believe neutrino to travel at the speed close to the speed of light, but we haven't measured it. I mean, yes.
Okay.
There is, I mean, any answer the physics gives you now is the answer till some degree. You can say for sure this is no. So neutrino have mass. So no massless neutrino are no. But to give answer yes, it's always a question of probability. So it's always statistics.
Thank you.
Okay. One more question over there.
Thank you for the talk. Could you explain a little more how does the Super Kamiokande works? Because I mean, if the neutrinos interact so weakly with the material that it has inside, how do you detect them? Because I mean, it will be difficult, I guess.
I mean, it is. The trick is that you just take a quantity. You take neutrinos and you take really a lot of it. I mean, by saying really a lot, it's like a lot. The amount of proton you usually strike on the target within the one physical run of T2K would be 10 to 19th power, so it's kind of a lot. I mean, it's a lot in our case, okay? In LHC experiments, there is a lot, there is more, but for us, it's a lot. And then, so first you throw a lot of neutrinos. Second, so something will interact for sure. And then when neutrino passes through Super-Kamiokande, then it creates a light of the Cherenkov cone. And that's what you detect, basically. So you just hope that out of all these neutrinos you throw into Super-Kamiokande, so in this gigantic tank of water, something will interact, and this will interact because neutrino will travel within the sorry, not neutrino, but the particles they will produce, so the electron or muon, they will travel faster than the speed of light in the water, because Super K is filled with water. Then it will create the cone of Cherenkov light, and that's what you detect. So with these things, that's something called the photomultiplier, which works like light bulb, but the other way around. So it takes the light, converts it to the electric energy, so to the electric signal. So you just hope that some of those you will see some sort of a cone signal here, and that's how you will see your neutrino. More or less like that.
Is it working? Yeah.
Yes. Will the dune experiment be effective in order to determine the velocity of the neutrino? Because if you know the moment where the collision happened and you know the distance, you can calculate the velocity, or it doesn't work like that? I
mean, yes and no. Yes, it can. No, not on the precision. It will be anyhow feasible to do in the light of our other experiments. But that's not exactly also it is not exactly the question which bothers scientists the most, so we invest less money given us by taxpayers into this question. So, I mean, yes and no. That's very ambiguous answer, sorry for that.
Okay, maybe I could say something about that. You have to remember that we are not dealing with classical mechanics. We are in a quantum world, and of course we are dealing also with relativistic speed, so it's not as easy as it could seem. So maybe that answers to your question. And there's another one. Okay, over there.
I was wondering about the differences in masses of between the flavors of neutrinos. Does that mean that if the neutrinos changes its flavor, changing the mass, does it mean that to conserve energy it changes velocity too?
Would you please repeat your question, because I think I'm not quite sure I understand what you want to ask.
I don't know if I understood correctly. If the neutrinos changes between oscillates between different masses, right?
It's not exactly oscillates between different masses. Okay, this is a little bit of abstract concept. The concept is the following: that neutrino oscillates between the types, being a mix of different masses. So it is a little bit weird. So, but it keeps the speed it goes.
Okay, so each type has the same mass.
Each type has the same mass. But you're trying to say that each neutrino, I mean, it's not like muon neutrino has this mass. You can say that this mass state has like this lies at this energy.
I mean, one neutrino that oscillates between types. Each time it visits one type, it has the same mass. It does not change mass while oscillating.
No, I would say no.
Okay. So I understood the okay, thanks.
Okay, maybe I can add something about that. You have to distinguish between flavor eigenstates that are the electron neutrino, mu neutrino, and tau neutrino, and the mass eigenstates. They are not the same. That's a point. More questions? Okay. Over there.
Thanks. A month ago, someone asked you about how to detect neutrinos, right? And you talk about using big masses of water to see the neutrinos interact. It's just to make sure. Some time ago, I heard about some detectors that were put in the ocean or in the sea. Does that have to see with wanting the water to interact with the neutrinos, or is something like that? I don't know.
Yes, that is called Freenet, the experiment which is also UVEG is involved with. It is in the Mediterranean Sea. And yes, so you need something. So this experiment, like so the Freenet, there are also experiments in the ice. They are made. The concept is the following: you have the Cherenkov light. So when the particle travels faster than the speed of light in the matter, then it creates some sort of this radiation. You know, this like how reactor, this nice blue color of light. That is called Cherenkov light. That's what it creates. Of course, you don't see the light in these detectors, but the PMT sees it. That's what's important. See detected. And yeah, I mean, material can be different. So it can be either water in the sea, or very pure water in Super K, or just the ice. The question is that then you will have to make a correction. The seawater is a bit different, and the pure water is a bit different. And that's all.
Okay, thanks.
Thanks for question.
Okay, so maybe we can finish at this point. Thank you again. It's been a very interesting talk, and of course, congratulations. And
thank you.
Yeah, okay. So if you have further questions or would like to discuss in detail something with any of the speakers, please send them an email so they can come by for the coffee breaks or something, and you can talk to them. That's one thing. Second thing, the coffee breaks. We will have a coffee break now just at the door of the faculty, right, after this talk, I think. And I think that's all. If I recall of something else, please, okay, yeah, important. If you have any problem, whatever it is, you have seen our faces, people who are taking care of the organization, just tell us, right, whatever it is. And there is also in this reception, you can ask for us there, because they have our phones, or they can get them somewhere. I won't be here the whole of the time, but you can get in touch with me easily. Okay. Thank you.
Hi. Okay. Can you listen to me? Thank you. Okay, I can here and here. Thank you.
So maybe we can start with our second talk. Our guest is Josu Sánchez. He's from Puerto de Sagunto, Valencia. He studied the degree in physics and a master in photonics here at the Universitat de València. Currently, he's developing his PhD studies under a fellowship contract guaranteed by the Spanish government. His research is based on the characterization of crystalline materials under extreme conditions for technological applications. And in particular, the topic for his talk is semiconductors under extreme conditions, experimental techniques. We are glad to have you here with us today, and now the floor is yours.
Thank you very much for inviting me to this school. I'm very glad to be here. And first of all, I want to say that I don't want this to be like a master class or something like that. I want to interact with you and more or less know what you know and see what you can feedback me. So let's start. Here we have the contents. First of all, we are going to see why do we do extreme condition physics. Then we are going to see our main experimental device that we use, that is the diamond anvil cell. There we are going to see what is a crystalline structure, and see what experimental techniques do we use to measure the physical properties of the crystalline material. And lastly, the conclusions. So first of all, I want to know what do you understand about extreme condition? What is to you extreme conditions? Pressure, temperature, okay. Anything else? Yeah, I think you got mainly to the point, so good job. We have high pressure and high temperature, so yeah, I mean, we have the materials at ambient conditions and they have properties, we can study them, but in the universe we have very different conditions. We have high pressure in the planets, in the stars, we have vacuum, so you also have to take into consideration low pressure and low temperature. You have 0 Kelvin and you can have a variety or range of things that you can measure. So high temperature is more or less straightforward. You heat your sample, you can have an oven, you can have a laser, you can beam it to a laser to give it a lot of temperature. So high pressure could be the challenge here, could be the thing that we are going to discuss more and see how we can apply high pressure. So first of all, we are going to define pressure. Pressure is the force that you are applying divided by the surface or the area. So just to make it clear, the force is going to be the weight of the book, okay? And the pressure is going to be that weight divided per unit of area, okay? So in order to apply high pressure, we don't need to have higher forces. I mean, we don't need devices that waste a lot of energy or you need to invest a lot of resources to get a high force. We can play with the area because the area is a geometrical thing, is something that you can control and you can get in your device, and then the problem you got is solved. So just to imagine someone on high heels, okay, can have a weight, and an elephant is going to have, for sure, more weight than a person. But this surface here is much more less than the foot of an elephant. So the pressure here on a high heel is going to be more than a pressure that an elephant is going to apply to you if it steps on you. So this is the main idea that we have when we want to develop or create something to apply high pressure. Okay, so now it's turn to answer this question. Why are we doing extreme condition physics? Can you tell me what ideas do you have? How can we use extreme conditions? Because we are studying this and we are discovering some things, but how can we apply this to real life? Or what can we discover? What can we develop? Throw any ideas to study space, okay? This planets, yeah. Deep sea, okay, that's another point. Okay, that's a really cool point. You're right. Yeah, yeah. Anything else? Okay, once I press the button, it's going to appear lots of things. So, are you ready? Yeah, I can go on? Okay. So, we have plenty of things that you were mentioning. Here we have the planetary science that you said, the superconductors, and the deep sea, also the biological living that are under high pressures. So mainly here we are focused on understanding purely how the materials are going to behave and the properties that are going to have under extreme conditions and how they are going to change maybe their ordering or their properties, but you can also have chemical reactions under high pressure that is going to be different from ambient conditions. You can also discover a new material that can be a really cool catalyst to have chemical reactions faster. And nowadays they are focused on the water splitting to split the hydrogen from the oxygen and get the hydrogen because it's a really powerful energy source. Okay. You can also understand how inside the planets or inside the stars the matter is behaving or how the material are forming. You can find super hard materials that can compete to the diamond, but this is really hard. And also something interesting, you don't have to go that high at pressure. You don't have to go to pressures close to the core of the planet. You can develop some food processing methods to preserve food for longer, and you can do that by high pressures, not that high from that, but it's something interesting. You don't have to always rely on matter. You can see food, or you can also see life. So it's a variety of range. This is huge. So this is everything from this question, and now we are going to get to the diamond anvil cell. So this is our main device. This is what we use mainly for all our experiments, and we have two diamonds here, a little two diamonds, carved like an anvil, and we put one against to the other to apply pressure. And in between, we put our experiment. We are going to get into that later. So we apply the force from outside. We can apply it by closing a screw or putting a membrane that is going to inflate with air step by step to increase pressure. And we have a little window to let some electromagnetic radiation to go through, and that's where we get the information from, because we can have everything inside, but if we are not looking inside in some way, it has no application. So the pressure that we can get from a conventional diamond anvil cell is going to go from 100 to 200 gigapascal. So 1 gigapascal is around 10,000 atmospheres. So 1 atmosphere is the pressure that we are having right now. So you have to multiply this by 10,000 and then add 2 zeros to more or less imagine what is the pressure that something that we put inside the diamond anvil cell is going to suffer. Okay, so we are going to get more into detail here. And we are getting back to the definition of the pressure. We said that we don't need high forces to get this pressure. We just need to have this surface to be really, really small. So you have it, the cullet is the part that is going to apply the pressure in the end, and this part is going to be from 100 to 500 micrometers. So it's really, really small in order to have really high pressures. Okay, so before going on, I want to ask, I just told you that those, we are using diamonds, but I know diamonds, I think you know that they are the hardest material on the earth, but why do we use diamonds in the end? There's also another reason why we are using diamonds. Why? Because of the structure of the diamond. But that's the idea, because the diamonds are transparent to a big range of electromagnetic part. So this little range is the visible light. We see here that the diamond can let it through, but also plenty of range in the infrared. So we can perform infrared experiments without any issue. Maybe we have some little windows that can be not that transparent, or maybe at the ultraviolet that we can try to invest on sapphire or other materials, but diamond is like the most perfect thing that we have, because it's the hardest one, it's the one that is going to preserve, is going to not break under high pressures, and also is going to be transparent. Okay, so let's get into detail here, and let's just start with this gray thing. What is the gray thing around the diamond? The diamonds here that have the green arrows, what is that? You can describe it by any words. You don't have to guess the proper word. I don't expect that, but why do we have this here? What is the purpose? Why? I mean, okay, can make that the pressure is uniform, that is right. And also, what else? There's something basic that we need this here. What? A wall. Yeah, we need something that contains our experiment. We don't need the experiment to go out or to go to any place, because if you are applying pressure, this is going to go away. So, yeah, this is called the gasket, and this is like a disc that first of all we have to indent. Is like to make the disc to have the shape of the diamond. So we put the disc in between without anything else, and we apply the pressure, and we make this shape. So we create not the chamber, but the thickness that we want. We also increase the hardness of the material, so it's going to preserve everything right. And then we took it off and make a hole by drilling with smashing electrons. It's a really cool device. But yeah, mainly this is the aim of the gasket. So we have the gasket, and then we have this little red dot here. I'm going to tell you this is not the main thing. This is not going to be the purple thing that I think you already know what it is. But we have something else. So experimentally, we need to control what happens, because we can do random things, but we need a controller. So what do you think is that? Exactly. We need a pressure indicator. We need to know which pressure we have inside, because we can go crazy and apply a lot of pressure and have really cool things measuring directly to the sample, but what pressure do we have? If we don't control the experiment, we don't have anything. So we have, mostly we use Ruby. We can use on other materials. It depends on the experiment. But if we point this with a laser, we are going to get the photoluminescence, this signal, and we can track this peak as the pressure goes up to see at which pressure we are. So we can start in here, but if we go to 10 GPa, this signal is going to move. So we can track pressure and we can know the pressure. So everything is controlled, everything is okay. Okay, now we have these two things, and I want to know this arrow here. What is pointing? It's not pointing to the middle thing, so what is this? What? Sample holder, more or less. Is something related? Do you have any other ideas? What is the blue thing around? A liquid, so it's the pressure medium. We cannot let our experiment to be in air, because if it's atmospheric air with common pressure, you're going to apply pressure and the hole is going to collapse and you don't have any experiment. And we also need the pressure to apply it evenly all around the experiment. So we need something that is going to be, its name, hydrostatic. So the pressure is applied evenly in all the directions. So we can have a solid one or liquid ones and also gases. So the more liquid that it is, so the gases, the more hydrostatic it's going to be. So knowing that, can you bet on which one is going to be most used at our experiments? What would you bet is going to be the most used here? The helium, okay, helium is a fair bet, is the smallest one, is a noble gas. It's going to be, has really cool results. Anyone wants to make a counter bet on any other one? Okay, so helium is really interesting. You can have really cool results, but it's a gas. So putting gas inside there, it's a really difficult thing, and it's really expensive. Also, helium itself is really expensive. So you can also take into account that if we want to repeat experiments over and over again, we need cheaper things and things easier to control. That's why we sometimes use methanol and ethanol mixtures. There are alcohols that we can mix easily and just have the hole open, put a drop of this, and then close it, and we are finished. It's not that easy. I mean, it's really small, and you can wash it all out. So, yeah, we use gases when you know I'm going. Okay, yeah. We use gases when we know that we are going to get really cool results and we need to go higher in pressure and have hydrostatic conditions, but they are expensive. So if we don't know what's going to happen or we don't know to go that high in pressure, we use liquids. Okay, and in the end, we have the sample. We have the main thing that we are going to measure. And I also show you a lot of things that we can measure, and here we usually measure crystalline materials. So here, I just wanted to notice something really cool. This is the structure of this material, of neodymium vanadate. This is a semiconductor. And this representation of the structure is the unit cell. I mean, it's the smallest thing that I can show you to explain the whole structure. And it's a tetragonal one. It means that all the angles of this kind of cube are 90, but it's not a cube. It's like a prism. The lengths of the bases are the same, but the height is different. So if you pay attention at this image, at this is a surface electronic microscopy. You see like the steps of a stair, right? You see macroscopically something that happens microscopically. You have something quantic reproducing macroscopically. So this crystal is really cool. I mean, for me this is amazing because I can see with my eye something related to microscopical properties. Okay? So we are getting into crystals, so let's define what a crystal is. So we have both here silicon oxide, and this is a crystal, this is quartz, and this is an amorphous material that is glass that we have in our windows. Which is the difference? The ordering. So if we have something ordered that we can get the unit part and we can repeat it by the properties that it has, we have a crystal. But if we have something that in short range can be repeated, you can see it here that is repeated, but at longer range it gets like random or gets away from the expected part, it's amorphous. Okay? And also inside the crystals, we can differentiate 3 different crystalline materials. We have a single crystal that we know that this piece is going to follow this ordering in the whole part. We can have polycrystals that are made of the same material, but the ordering is going to have by regions. This region have this orientation, this other region have other orientation, so it's not that ordered like the single crystal. And we can also have powder. So the powder, each grain is going to be crystalline, but you have a lot of parts that are going to be random, so we can have either of these 3 things. And one thing that we want to discover or we want to know is the structure of this, because I already showed you the structure of the neodymium vanadate, but we can have a material that is new, but that we don't know the structure, and we want to solve this structure and to know the properties of how this unit cell is explained. Okay, so that's why are we getting to the Bragg's law. The Bragg's law is this condition that says if we have an ordered structure that has some planes that have this distance that is going to be d, we can light the planes with a light source that has this wavelength, and if we complete this condition with a proper angle, we are going to get diffraction. So this is going to be diffracted and we're going to have the red part. If we are not completing the Bragg condition, we are not going to get any feedback from the structure. Okay? So if we perform what is called an X-ray diffraction experiment, we're going to see moving in angle. We are going to make a range in angle. We're going to see the peaks that are going to show that are diffracted. So if we put a glass that is something amorphous, the distances are going to be around here, but not well defined. So we're going to get a huge range of distances that are going to complete the Bragg condition. But as you see, this signal is quite noisy, so it's something blurry. We are not going to get much more information from this. But if we have something crystalline, we can get the phases of the quartz. And we can also differentiate the phases. So this phase, it's pretty similar to, the alpha is pretty similar to the beta one, but if you see here, maybe one is displaced to the other, but here we have an extra peak. You see, so those phases are different, okay? I think these are more or less self-explaining, but I found a really cool GIF that I can show you here, and you can understand better the diffraction. So we have the monochromatic X-ray source that is beaming into the sample. Here we have a polycrystalline or a powder sample, and we have the detector that is going to move with the sample. So this XRD device is like the simplest one that you can have. We are using other ones that can get more signal or can get other properties. But here, as you see, we have an orientation, a way of the grains are getting, has this orientation, this structure, crystalline structure, and once we get to these orientations, we get the peak. Okay, so we make the range to try to find the peaks. So what would happen if we have a single crystal? So here we're having something like a powder or a polycrystal. What will happen if we put a single crystal? We are going only see peaks from this direction or this proper orientation. So having single crystals can give you more information about the orientation of the crystal. So single crystal X-ray diffraction is used to orientate the sample and to use it for other purposes, for other experiments, but we can use that. Okay, so this is characterized. We can move on to other properties. So in the material, we also have vibrational modes. We already know that everything is oriented, everything is located where it has to be, and we have temperature. So this is the bonds or the location are going to move, are going to vibrate. So we have several types, ways of vibrating. Here we have 3 points or 3 atoms. So the more atoms we have, the more combinations and things are we going to find. So we have the symmetrical stretch. We get 1 point, and the atoms outside this point is going to vibrate symmetrically. It can vibrate also asymmetrically. And we can have some bonds. The bonds are not going to stretch or change, but the angle between the bonds are going to change. This is a bending. And we can also choose one axis of the classification or orientation of the crystal, and we can make like a little move around this axis, so we can have these librations. Okay, so there is an experiment that can get this information. Do you know what it's called? Infrared, yeah, could be. It's we also use another one. It rings a bell for you, but you're right. Infrared can get us this, but it's more. I'm going to explain one that is going to be difficult to explain, but infrared is even more difficult. So this is the Raman spectroscopy, the Raman effect. Okay, so in the Raman effect, you have to understand that once you light one sample with a coherent source, like with a wavelength, like a laser, mainly all the photons that this structure is going to absorb, the structure is going to re-emit those photons elastically, I mean, with the same wavelength. It's going to say, okay, you give me that, I'm going to give you back everything that you gave me without changing anything. But then you have one effect, the Stokes effect, and you also have the anti-Stokes effect, that this energy that you're giving me is close to the energy that I need to excite one of the vibrations that I told you. So I'm going to use this energy to excite this vibration, and then I'm going to give you back this energy that I used. And this energy is going to be different from the one that you gave me previously. So in order to let you know what intensity has these events, it's 1,000,000 times less than the energy source that you're using. And that's why having this guy, Raman, an Indian person from last century, discovering this, a really little effect, this is really impressive. So nowadays we have laser sources that can provide us plenty of energy, and then we can see the Raman effect more or less with some resolution. But this is an effect that is really small. So more or less this is the setup. You have a laser, you focus the laser into the sample reflects the laser. This notch filter is going to take away the laser part, because as I told you, if you have a spectrum that has the laser and some Raman things that is 1,000,000 times less, you're not going to see anything. So you have to take the laser away with the notch part and get the contribution of each wave number with a spectrometer. Okay? Did you get everything? Do you have any doubt? This is pretty advanced. I'm trying to simplify everything. I'm getting lots of things out of the talk, but I'm glad that you're getting everything. Okay, So let's get to another, well, before going to that, this is an example of a Raman spectrum. This is iron vanadate. It has this structure. It's a triclinic structure. It's the most asymmetric one that you can find. You have the 3 angles that you have are different, and the 3 directions are different. So everything is different. You don't have any symmetry. So the way of vibrating, you have the phonons. It's like the unity of a vibration. You have 54 asymmetric and 54 symmetric. So the Raman ones are going to get the symmetric ones, and as you said, the infrared is going to get some of the antisymmetric ones. And you also have some silent that both cannot get. So here in this Raman spectrum, we are getting, or we are solving 43 of the 54 that we can find. This is hard. This is a mess, so you have to be careful with this and to move on. But yeah, experimentally, when you are at the lab, everything is funny, and I really enjoy myself at the lab. But once I get to the computer and I have to solve those things, I'm like, come on, why do I have to solve this triclinic thing? This is so difficult. I hope in the future someone will use that, because I did a lot of effort to do that. Okay. So in the title I said semiconductors, and I'm not talking too much about the semiconductors, so let's give a brief talk about this. So can you recognize this? What? Yeah. So you know things about the band gap, more or less? Okay, I'm glad, because sometimes it gets difficult. So you have the orbitals or the energy states of a material, and if the energy states of valence, I mean the ones that you can get from the electrons that you have in your structure, are completed, those electrons cannot go anywhere. It stays there, so this is an insulator. You don't have any charge. But if those states of valence you have some parts that you can go, or you have not completed, it's half empty, you can move from others, and you can have like the electron cloud, and you have some way to conduct. So the semiconductor is the one that you have the valence band full, you have the conducting band empty, and the jump that you need to make to go to the conducting band is short, let's say. The energy that you need is that short. So experimentally, we can measure this band gap, and it's interesting because we can know the band gap of the semiconductor, and we then can more or less guess which applications is suitable. Okay, so we can use absorption spectroscopy. We have a lamp of light that is going to be focused on the diamond anvil cell on our sample. Then it's going to go to the spectrometer and get back to. So this is simpler than the Raman and the XRD, and we have some prism to look inside and to change positions, because in order to get absorption, we have to compare the light that goes through the pressure transmitting medium and the light that goes through the sample. So we have 2 spectrums. And once we compare them with the VN law of absorption, we get the absorption spectrum. Okay? So one thing before going, why do I have here a laser? But I want the absorption range. I want something that is wide. I don't want it to be like coherent or monochromatic. I don't need it. That's why I'm using a halogen lamp. But I need a laser for my experiment. Why? I told it before. I just wanted to let what? Because the high energy of a laser. No, I mean for the absorption patterns, I need the halogen lamp. The laser is for another thing. That's it. That's it. So 10 points for your group. I need the laser for the ruby. I need to change. Sometimes I need to get the pattern and then change back to the laser and see what pressure do I have inside to attach the pressure that I have with the pattern that I'm getting. Okay? So good job there. And these are the results that I'm getting. This is just the part that is interesting for me, because in the absorption thing I can have like a really weird shape, but we have the absorption tail, and I can fit this tail with the Urbach law and get the energy band gap. So this is again the iron vanadate. This is the starting of the experiment. I have here the sample. This is the hole of the gasket. We have around some methanol-ethanol water mixture, and this is the ruby, and we have some other rubies around, but the rubies are used just for the getting the pressure. So we started more or less here, and here we have a band gap that is going to be close to making here a line. So we are getting something like 2.4 electron volts, something like that, and we're going up in pressure. But what happens here? Once I get close to 2 GPa, the sample changes abruptly. It makes this jump. It goes from 1.46 to 2.17 from here to here. And the energy band gap is totally changed. Why this happens? What? It's getting to a metal, but why? It's metallizing more or less. That's it, because it suffered a phase transition. The structure is totally changed. This is something that you're going to explore more in the next talk with Robin. He's a workmate. He's going to talk more about phase transitions, but yeah, we went from yellow to like red-brown thing, and the band gap collapsed. If I apply more pressure, this band gap is going to collapse more and more, up to a point that it suffers another phase transition that totally smash the sample, make it like powder, and I can no longer get any absorption pattern, because I need a huge spot to get the pattern. So here is perfect. Here I had some troubles to get a proper spot, because I need something like this ruby, but not that big. But here is impossible. I cannot have anything there. And if I keep the point C if I keep applying pressure. But if I stop here and I go back to ambient pressure, I have the D part. The D part, you see something that is partly smashed, but it comes back to the yellow. That's why this phase transition is reversible. It only exists under high pressure conditions. Okay? If I go back to ambient conditions, I no longer have this phase. But it's cracked because you can no longer make again the bonds that you had. You know. Fully reversible in the means of orienting. So the orientation, you start this orientation, then you change to another, and once you go back, you go back. This is a microscopical property. Macroscopically, you cannot form back the things that you broke. Okay, it's just the material that is made. Okay, and you also have other materials that are non-reversible. I mean, you get a new phase transition, and once you go back, you don't go to the previous transition. Can you guess any of that? That's something that I was mentioning the whole presentation that I use a lot. Yeah, the diamond. So diamond is a metastable phase. It's not something that you get naturally. Well, you can get it naturally, but it's if you apply high pressure and high temperature. So yeah, you can find some new materials that can get really interesting properties like the diamond and have new technologies based on that. Okay? Yeah, I'm on time. So in conclusion, we have discovered the potential of the how we apply extreme condition physics. We have learned how the diamond and cell work, and we have seen some relevant properties of the crystals and the techniques that are used for measure them. Okay, so thank you for your attention.
So, thank you very much. It's been very interesting, even for a theorist.
Thank you.
So now it's time for questions. You have.
I think I didn't let much time to questions,
Yeah.
but we interacted a lot, so.
Yeah, that's true.
Hi. First of all, really nice talk.
Thank you.
Can you go back to the absorption spectroscopy slide?
The setup?
Yeah, this one. No, the crystal one.
Okay.
As you mentioned that you need a very specific spot size to measure. So is it possible to go even smaller with better equipment or not?
Of course. I mean, this is limited to the lens and the pinhole that we are using for focusing here.
Yes.
So if I have a device that can focus it better, I will have better results. Or also if I have a super continuum source that is close to, you're using a fiber optic to get that, and then the spot is small, I can have smaller parts, of course.
Yes, so is it part of like future research, or will it be?
It depends on your lab. I mean, you're working on a lab, and you have your material, and you have to adjust to the things that you have. So if we think that we can improve our results by having a smaller spot, then we are going to invest our resources and money to get this smaller spot. But maybe we need other devices or other techniques. So you have to consider everything.
And also I don't see any scale, so what is the scale here? Like how
the scale, this hole is half of the culet size. So if this experiment, I'm using a culet of 200 microns, so this hole is going to be 100 microns, more or less. So this sample is going to be 40, 50 microns.
Yeah, that's big. Okay.
That's quite small, and you have to put it by hand.
No, actually,
under the microscope. So yeah, you think that you are being steady, and once you get in the microscope, it's like you're like, come on, what is happening?
Yeah, that was my question. Okay, thanks.
Thank you.
We don't have too much time for questions, so
I'm sorry.
Can
I can give you my email if you want to.
Okay, when you get the second type, like the B one, how can you like extract it? How can you conserve the structure or this condition to use it, like to do XRD on it or to do other analysis, or how to use it? Do you have a way or a technique to conserve this pressure or this structure?
This is inside a diamond anvil cell, so I can find this with absorption, and then I can repeat my experiment, but instead of being under the absorption setup, it's under the XRD setup. So I can repeat it, because I expect this to happen every time I get to this pressure. So it's reproducible every time. Thank you.
So now it's time for coffee break. If you have any more questions to Yosu, you can...
I'll be there.
Yeah. And we'll see you at 11:30.
Thank you. Oh, such a relief.
Yeah, you can relax now. I'm in the worst bit because